f of x equals to x squared minus 2 divided by x, and we want to perform a second derivative test, the procedure is written down below. So first we need to find f prime and f double prime, and then we set the f prime equals to 0 and then solve for x, and then we test the critical number using the double prime, and then we will reach to our conclusion. So the function is x squared minus 2 times x to the negative 1 power, and then the first derivative, that is equals to 2x, bring the negative 1 down, you have a positive 2, and then negative 1 minus 1 is equals to negative 2. And then you set the first derivative equals to 0, and then you solve for x. So we have a 2x plus 2 divided by x squared equals to 0, and then we get a common denominator. For the 2x, you multiply top and bottom by x squared, so 2x times x squared is 2x to the third plus 2 equals to 0. You have top divided by the bottom equals to 0. So since we have a reciprocal, since we have an x in the denominator, that's why in the original function, I have to specify that x can never be equal to 0, because I don't want to pick a 0 and then test that at the end. So you have a top divided by bottom equals to 0. That means the top has to be equal to 0. Plus 2. Is this possible? Let's solve it. So we have x to the third equals to negative 2 divided by 2, that is equals to negative 1, right? So x to the third equals to negative 1. So what is x equals to? 1 or negative 1? 1 times 1 times 1 is not negative 1. But negative 1 times itself 3 times is equals to negative 1. So that means x is equals to negative 1, and this is my critical number. Okay, compare this to the domain of f. Do we have any contradiction? The answer is no. I only don't want a 0, so negative 1, I'm okay with that, because when x is equals to negative 1, the function is defined. So let's proceed to the second derivative, so double prime. So I would start right here, right? So based on the first prime. So the derivative of 2x is equals to 2. You bring the negative 2 down, so you have a negative 4, and then x to the negative 3. All right, and then what happened when x is equals to negative 1, double prime? When x is equals to negative 1, 2 minus 4 times negative 1 raised to the third power. So you still have a negative in the denominator, but the negative and the minus becomes a positive. So you have a 2 minus 4 and then negative 1, right? So that is 2 plus 4 divided by 1, that is equals to 6. 6 is positive. Second derivative positive. What does that mean? That means the function is concave up at this point. Concave up. Now, let me give you the concept of second derivative test using a picture. So first of all, we found the first derivative, set that equals to 0, and then we got negative 1 as my critical number. So that means when x is equals to negative 1, so x is equals to negative 1, first derivative equals to 0, that means we have a horizontal tangent line. All right, we have a horizontal tangent line. And then at this point, you test this point using the second derivative, and you get a positive concave up. That means based on this point, we have a concave up curve. Now, at this point, we have a concave up curve. Is this point minimum or maximum? So it turns out that this point is a relative minimum. And some textbook call this local minimum. And then that's it. So there is a relative minimum at x equals to negative 1. So what is the exact location? The exact location is f of negative 1. So that is equals to negative 1 squared. We plug it into the original function. Actually, let me just use a different color so you don't mix this up with the parabola, with the derivatives. So f of negative 1, so that is equals to negative 1 squared minus 2 divided by negative 1. So we have a 1 plus 2 divided by 1, right? So we have a 1 plus 2 divided by 1, that is equals to 3. So that tells me negative 1 comma 3 is a minimum. It's a relative minimum. Can we verify this using a picture? The answer is absolutely yes. So I already prepared a picture for you. So in this picture, do you see that at negative 1 comma 3, we have a relative minimum? And then what happened when x is equals to 0? When x is equals to 0, there is a vertical asymptote, right? So there is a vertical asymptote when x is equals to 0. And then on the right hand side of the vertical asymptote, that point has no min, no max, just a function that is always increasing. Alright, so that is the end of this video. If you think my instruction is clear and helpful, give me a like, share this video in any social media for me. If you are new to the channel, please take 2 seconds to click the red subscribe button down below. I highly appreciate your help. I will catch you all in the next lesson. Signing out.